Let's talk about sensors, the hidden gems in the modern world. The new podcast series from Dr. Block, brought to you by All About Sensors. It's Season 1, Episode 4. Dr. Block explains how barometric pressure sensors help to increase height information, brought to you by All About Sensors.
You rely on GPS for navigation constantly, right? I mean, we all do.
Absolutely, yeah.
But have you ever noticed it can get a bit, fuzzy when it comes to telling you exactly how high you are?
Oh, definitely. That vertical accuracy is notoriously tricky.
I've definitely had my GPS tell me I'm on the wrong floor in a parking garage. It's kind of weird.
Yeah, that's a classic example. The Global Navigation Satellite System, or GNSS, which, includes GPS, often struggles with what we call vertical accuracy degradation.
Right. Degradation?
It's partly down to the satellite geometry, the angles. The vertical error margins are just inherently larger than the horizontal ones.
Okay, so it's baked into the system almost.
To an extent, yes.
Right.
And then you add factors like signals bouncing off buildings, it's multipath, or even interference from the atmosphere, the ionosphere. It just makes it even harder to really pinpoint your exact altitude. Yeah. These aren't just tiny glitches, they can be persistent errors.
Which is why this deep dive is so interesting. We're looking at a recent IE Sensors Journal article, and it unveils a really novel approach. Researchers use a simple, pretty low-cost sensor, a barometer, but in a completely unexpected way.
Exactly. To dramatically improve altitude estimation, especially in those really challenging spots like dense cities.
So, okay, using a barometer for altitude. That feels like a natural fit, doesn't it? Pressure changes with height. We all learned that.
Right. It seems obvious.
But what were the sort of traditional ways of mixing barometer data with GNSS, and why haven't they fully cracked this vertical problem?
Well, traditionally, these barometric altitude correction, or BAC methods, they basically treated the barometer as an altitude reference point.
Okay.
One way was trying absolute altitude estimation. So directly converting the air pressure reading to an absolute height using standard model.
Like sea level pressure and all that.
Exactly. But the big challenge there is you need a really accurate sea level pressure reading right now, and that fluctuates constantly with the weather.
Ah, right. Okay.
Plus, you also have to deal with the difference between the sort of smooth mathematical Earth model, the ellipsoid, and the actual bumpy surface, the geoid. These assumptions just don't hold up well for precise low-altitude stuff.
So trying to get an absolute number was kind of a non-starter for many applications. What about just tracking changes?
That led to the second approach, relative altitude estimation. Basically, tracking height changes from some starting point, a reference point.
Seems more manageable.
It avoids some of the absolute issues, yes. But, and this is the key problem, it inevitably accumulates drift error over time.
Drift error? How so?
Because that reference pressure you started with, it changes too, subtly, because of weather shifts. So even over short periods, like in the preliminary tests mentioned in the article, if you started on one floor and came back, the system would often think you ended up at a slightly different height.
Ah, I see. So even if you come back to the exact same spot, the barometer reading might have drifted, messing up the calculation.
Precisely. That drift is a real persistent headache in these traditional methods.
Okay, so wait. If the barometers themselves drift, how did these researchers get around that? That sounds like the core issue. What's their big idea?
This is where it gets really clever. The proposed method, barometric velocity correction, or BVC, takes a totally different perspective.
Okay.
Instead of using the barometer data as an altitude or displacement reference, they treat it as odometric data, like an odometer in a car, but for vertical velocity.
Velocity, not height change.
Exactly, vertical velocity. The key insight is converting those pressure measurements directly into how fast you're moving up or down.
Okay, how does that help?
They integrate this velocity information into a common framework called an extended Kalman filter, or EKF. But crucially, and this is the game changer, the reference pressure they use for this velocity calculation isn't fixed. It's dynamically updated in every single time step.
Ah, so it's constantly reevaluating the baseline, not just sticking to that initial reading that might be drifting away.
You got it. Unlike errors in measuring displacement or height change, errors in measuring velocity don't accumulate in the same way over time.
Right. If you misjudge your speed for a second, it doesn't mean your total distance is permanently wrong. You just correct it next second.
Sort of, yeah. This dynamic updating effectively cancels out that common drift problem that plagued the older methods. It makes the whole system much more robust.
Okay, that makes conceptual sense. So what does this actually mean for accuracy? Out in the real world, how much better is it?
Well, the results they presented are pretty compelling.
Lay them on us.
Okay, using simulated data first, where they could control everything, BBC significantly improved altitude accuracy. We're talking reducing vertical errors by up to 27.6% compared to the conventional BAC methods.
Wow, over a quarter better. That's substantial.
It is. And it also proved much more robust when they intentionally introduced things like barometric bias or simulated poor GNSS conditions. It handled the errors better.
Okay, simulations are one thing. What about messy reality, like cities?
Right. So real-world data. Testbed 1 was in a complex urban environment. Lots of GNSS noise, buildings, frequent ups and downs.
The ultimate challenge, really.
Pretty much. And BBC performed really well. Yeah. It accurately captured the initial movements and, importantly, maintained a stable estimation even when the GNSS signal suddenly went haywire, which happens a lot in cities.
Did it find its way back? That loop closure test?
Yes, it achieved reliable loop closure. So ending up back very close to the starting altitude. Meanwhile, GNSS only, or the traditional BAC methods, they showed significant instabilities and ended up with big altitude differences.
That's a huge practical difference for navigating cities or for drones flying between buildings.
Absolutely.
Did they test it anywhere else, like less chaotic places?
They did. Testbed 2 was an open field scenario, but with varied slopes going up and down hills. Even there, BBC still showed superior loop closure.
Interesting.
And it avoided a specific problem. The old methods had sometimes they'd undershoot the altitude estimate during rapid vertical changes, like going quickly downhill. BBC handled those transitions more smoothly.
So it seems more stable across different environments.
Exactly. And what's really neat is the system's adaptive intelligence. They looked at something called the Kalman gain.
Which is basically how much the system trusts each sensor input, right?
Yeah. The analysis showed the system dynamically adjusts its confidence. When the GNSS signal gets weak or unreliable, like between tall buildings, it automatically starts trusting the barometric velocity data more.
So it intelligently fuses the information, leaning on the barometer when GPS falters.
Precisely. It's a smart adaptive fusion.
This deep dive really highlights how sometimes a fresh look at a simple, common sensor like the barometer in your phone can unlock huge improvements. Rethinking the data from height to velocity seems key.
It really is. And this isn't just academic. It's vital for improving things like autonomous vehicle navigation, drone operations, even just getting better location services on the devices you use every day, especially in those tricky urban canyons. Precise vertical location is becoming critical.
Absolutely. It's amazing how much potential can be hidden in plain sight.
And it leaves us with a really interesting thought, doesn't it? Considering how often technology finds new uses for old parts, what other seemingly simple or maybe even old sensors are just sitting there, hiding unexpected potential? Just waiting for someone to look at their data in a completely new way and unlock their power for whatever comes next.
Thanks for watching. I hope you liked it or learned new things. Please also visit me on X, Instagram, or read my blog articles on WordPress. Bye.